Welcome to Up Close, the research, opinion and analysis podcast from the University of Melbourne, Australia.
I'm Shane Huntington. Thanks for joining us. The modern-day telescope is nothing like the refractor used by Galileo to discover Jupiter's 4 largest moons some 400 years ago. Today, increasingly sophisticated telescopes, some of which now orbit the Earth, detect not only visible light, but also frequencies at the far ends of the electromagnetic spectrum. The silent radio waves and gamma rays that these instruments detect allow us to explore the universe in a way Galileo could have only dreamed about. They have painted for us a picture of the universe that extends back in time to when the universe first began. Our view of the heavens is far from complete, however, and our relentless search for understanding over the past century in particular has meant that physicists are being constantly challenged to find theories to fit their observations and observations to fit their theories. Our guest today on Up Close, Professor Lawrence Krauss, is a theoretical physicist and one of the first to suggest that most of the energy of the universe resides in empty space and is unseen, a concept now referred to as dark energy. Lawrence Krauss is Foundation Professor of the School of Earth and Space Exploration and Physics Department, co-director of the Cosmology Institute and director of the Origins Project at Arizona State University. He is a visiting Magunya Fellow here at the University of Melbourne. Welcome to Up Close, Lawrence.
It's a pleasure to be here.
Now, Lawrence, today when we talk about the universe, sooner or later, the topic of the Big Bang seems to enter the picture. How did we come about this particular concept and what does it actually mean?
Well, the Big Bang actually was forced upon scientists. In the turn of the last century, the conventional scientific wisdom was that the universe was static and eternal. It sort of looks that way. When you look up at the night sky, it's the same night after night, and it seemed to be a reasonable explanation for things. And through a series of initially sort of theoretical constructs, it was realized that it's very difficult to have a static universe. And Newton tells us why, because gravity sucks. And you put a bunch of stars out there, and they all tend to collapse together by their gravitational attraction, and it's very difficult to have a static universe. But what's important to emphasize is that science is an empirical discipline, and what really forced the realization the universe is expanding was observation and experiment. And the first key observation was made by Edwin Hubble in 1929, that as we look around us, all galaxies are receding. On average, they're moving away from us. And what's even stranger is that those that are twice as far away from us are moving twice as fast, and 3 times as far away from us, 3 times as fast. And of course, when you think about that, it tells you immediately that we're the center of the universe, right? But that's not true. That's just because of our myopic place in the universe. What it really means is that the universe is expanding. And of course, if the universe is expanding, you work backwards. It was once smaller. You keep working backwards. And once you can show that everything we see in the universe today was once together in a single point, smaller than the size of an individual atom. It's almost impossible to comprehend that, but that's the way it was.
As humans, it's very hard for us to picture timeframes that are beyond their own life cycle. And even in the sort of geological sense on Earth, it's very hard to picture these. What kind of time frame are we talking about for the Big Bang?
Well, we're talking about a very long time. And what is amazing, in fact, is we now know that time to great accuracy. I would not have thought it would be possible in my lifetime. We now know that the Big Bang occurred 13.72 billion years ago. Billion years ago. That's the age of the universe in most places except some American states where it's still 6,000 years. But in the real world, it's 13.72 billion years. And that means that our sun, by the way, and Earth are relative newcomers. Our sun and Earth are only about 4.5 billion years old.
In terms of actual physical evidence for the Big Bang itself, what is there that we can see at the moment?
Well, there are 3 main pillars of the Big Bang. One was the discovery by Hubble that the universe is expanding, that galaxies are moving apart. That's profound evidence that the universe is getting bigger and was once smaller. Based on that, we can work backwards with our physics. And by the way, that means when we look out at the universe, we're doing cosmic archaeology. We are looking back in time. When I look at you, I'm actually looking back in time. It's just a fraction of a second for the light to get from you to me, but it's back in time. But when I look at a galaxy that's 1 billion light years away, I'm looking back 1 billion years ago. And that means when I see distant galaxies that are 5 billion light years away, I'm actually not only looking at light that was emitted before our sun and Earth formed, but the stars that I'm now seeing probably don't exist anymore. So as we look back in time, we would expect to be looking back closer to the Big Bang. And if we work our physics back, we find that as the universe was smaller and smaller and smaller, it was hotter and hotter and hotter. And back at a time when the universe was about 100,000 years old, the universe was so dense and hot that matter got stripped of its electrons. The radiation would break apart neutral atoms of hydrogen, and you'd have a dense plasma. And a dense plasma is opaque to radiation. You can't see through it. So if we look back far enough, a prediction of the Big Bang is that we should basically see that surface when the universe first became transparent and all that radiation came towards us. Just like in this room, I can see the walls because light bounces off the walls and comes to my eyes because the room is transparent. Once the universe became transparent, that radiation started coming towards us. So a prediction of the Big Bang is that there should be radiation coming at us from all directions. It's cooled as the universe is cooled. It was 3,000 degrees then. It's 3 degrees now. We see that radiation. It's called the cosmic microwave background radiation. It was discovered by accident in New Jersey by two people who didn't know what the heck they were doing, but they won the Nobel Prize nevertheless. So the discovery of the cosmic microwave background really confirmed that the early universe was hot and dense. The expanding universe tells us it's expanding. And the last real pillar of the Big Bang takes us back to a time when the universe was 1 second old. At that time, the temperature of the universe was about 10 billion degrees. It was hot enough for nuclear reactions to occur with abandon. And based on experiments in the laboratory here, where we measure the rate of nuclear reactions, we can predict at those early times what abundance of light elements was formed. At that time, before that time, there were no elements. After that time, the light elements hydrogen, helium, and lithium were created in that first few seconds or first few minutes of the Big Bang. And the predicted abundance of those elements varies by 10 orders of magnitude. When we look out at the universe, we discover, bang on, 25% of the universe is predicted to be helium. That's what we see. 1 part in 10 billion is lithium. That's what we see. And by the way, for your listeners, all the other elements that really are important for your life, the carbon, nitrogen, oxygen, iron, all those things were created much later in the dense cores of stars which exploded. So you're really stardust.
Now, Lawrence, when we look back over the last 100 or even few hundred years, we see initially physics through Newton had a certain view of the universe, and then Einstein and all that period around Einstein's discoveries around the early 20th century gave us a different view of the universe. What's the current model at the moment for how the universe works? And I realize this could be a question that would take a month to answer.
Yes, there's many aspects of the model of how the universe works. And I should say, we don't have a complete understanding. In fact, that's the great thing. There are mysteries remaining to be solved. And in fact, one of the biggest mysteries in physics was based on a relatively recent discovery, which you alluded to, that our model of the universe is one in which, by the way, we are much more insignificant than we might have thought before. Because you can take all of the matter that we can see in the universe today with telescopes, the galaxies, stars, planets, any aliens, everything that's out there that we think of as a beautiful universe, you get rid of that, all of that, and the universe is largely the same. Everything we can see and everything we're made up of is literally a 1% bit of pollution in a universe full of dark matter and dark energy. What are those things? Well, dark matter, when we try and weigh galaxies, which we've been able to do, we'd find out that basically there's 30 to 40 times as much stuff out there as meets the eye. So much stuff that our very successful calculations of the abundance of light elements tell us there aren't enough protons and neutrons in the universe to account for all that stuff. It must be some new type of elementary particle, which means it's not just out there, it's going through your body right now as you're talking to me and going right through the Earth. That means we can actually do experiments here on Earth to look for it. So we don't know what it is. We think it's some new type of elementary particle, but there's a lot more of it than there is normal stuff. And as wild as that is, what we've discovered is even that is just the tip of a cosmic iceberg. Most of the energy in the universe resides literally in empty space. Empty space weighs something, and we don't have the slightest idea why it's there. But when you add up all of that energy, what you find is that the universe we live in is what's called a flat universe. Einstein told us that matter can curve space, and our universe could live in one of several different geometries as a result. In fact, the reason I got into cosmology was in some sense to be the first person to know how the universe would end. I thought it seemed like a good idea at the time. Because a closed universe, if it's full of matter, a closed universe is one, if you look far enough in one direction, you'll actually see the back of your head. Space will close on itself. This is a three-dimensional closed universe, not a two-dimensional one, so it's very hard to picture. But that would be the way it would be. Such a universe, if it's full of matter, will expand, stop, and recollapse. An open universe will keep on expanding forever at a finite rate, and a flat universe is just at the boundary between the two. And, once we discovered the fact that the universe was expanding, that became the holy grail of cosmology. Will that expansion end? And to know whether it would end, we had to know the geometry of the universe, and that means we had to know how much stuff there was. And now that the dust has settled, we found we live in a flat universe, which is kind of the one that theorists like me thought we lived in, because it's the only mathematically beautiful universe. And we have ideas about why the universe may be flat, but we were astounded to discover that the reason there's enough energy to make the universe flat is that energy resides in empty space, and it's still a mystery.
Do we know whether that expansion at the moment is sort of accelerating or decelerating?
Well, in fact, the reason we know there's energy in empty space is precisely from that observation. As I said, gravity sucks, so the universe should have been slowing down, and astronomers looked out to try and measure the rate at which the universe was slowing down for a long time. And much to their amazement, what they discovered as we look at distant objects, that the universe is actually speeding up. And there's only one way that could happen. Well, there are two ways. One, the observations could be wrong, but they don't look like they are. The other way is that, in fact, there's energy in empty space, because the only place to get gravitational repulsion, anti-gravity, if you will, is if you put energy in empty space. And amazingly, if you add just the right amount of energy in empty space to the amount of energy in dark matter, you get a flat universe, which we've independently measured to be the case. So we needed that dark energy anyway, but it is causing the expansion of the universe to accelerate. And that means, by the way, that the future is going to be very different than we thought it would have been.
For some years, there was a lot of excitement around the area of string theory. Is that something that now is off the boil?
Well, I think it depends who you talk to. In theoretical physics, one of the areas where we really still don't have a handle is when you take very small scales, where quantum mechanics is important. It turns out Einstein's general relativity is inconsistent with quantum mechanics. We can't put the two together. And that means to understand the quantum mechanics of space and time, which is really what general relativity is a theory of, on very small scales, we need a new theory. And string theory was proposed to be such a theory. And of course, it's a very exciting idea. One of the side implications of it, however, is that there must be many extra dimensions, and you have to get rid of them by curling them up on a scale so small you can't see them. And it is still a very attractive and interesting idea. The problem with it is that it's become very complex, and it's not clear that it has anything to do with reality. The hope that it would lead us to a theory of everything has certainly not been realized. That does not mean it's wrong. It just means that it hasn't made the kind of progress people hope for, and in fact, it really has not yet made any real contact with experiment. And that means that it may not describe the universe in which we live. And once again, I want to remind people that physics, even cosmology, is an experimental science. And unless you can test an idea, it really isn't scientific.
This is Up Close, coming to you from the University of Melbourne, Australia. I'm Shane Huntington. Our guest today is Professor Lawrence Krauss, and we're talking about the origins and future of the universe. Lawrence, when we look out into the universe at the moment, as you say, we can go back a fair way in time. We can look at so many different objects in different wavelengths. Are there objects out there that we just don't understand in terms of how they work at the moment?
Well, yeah, there's a lot we don't understand about the universe. There's a lot we do. And every time we open a new window on the universe, we're surprised. There are lots of puzzles. I'll give you a recent example of a recent discovery. We know now that at the center of most galaxies are huge black holes. Black holes are objects that are collapsed matter that's so dense that light can't even escape from them. They're probably the most exotic gravitational objects in the universe. And at the center of most of our galaxies there are million or billion solar mass black holes today. Nowadays we can sort of think they formed from things collapsing and stars merging, but in the earliest moments of the formation of structure in the universe, in the first billion years of the universe, or for a few hundred million years, we would have thought that objects, small objects like stars would form and such. But what's recently been discovered is evidence for supermassive black holes, even in the earliest structures of the universe. How did they form is a mystery. And in fact, it's a chicken and egg. We don't know whether the existence of these supermassive black holes are necessary for galaxies to form around them, or whether the galaxies were necessary for the formation of the supermassive black holes. So that's one of the reasons we want to actually build the successor to the Hubble Space Telescope, which is called the James Webb Space Telescope. And unfortunately, it's in precarious ground. With cost overruns, there's discussions of canceling the project. It would be devastating to the future of astronomy and science if we did. So that's one example on large scales. On small scales, there's a tremendous amount we don't know, which is why we built the Large Hadron Collider, which is now running in Geneva. And there's this beautiful synergy, by the way, between particle physics and cosmology, which is where I work. Because if the universe is expanding, that means everything was once contained in a region which is very small. That means in order to understand how it got to be that way, we have to understand the physics of the very small, which is where we're exploring it at accelerators like the Large Hadron Collider. And there we're trying to understand why particles have mass, a whole bunch of questions related to, ultimately, the question of how we got here. Ultimately, all these questions come down to the same questions that people asked themselves when they were growing up. How did we get here? Where do we come from? Where are we going? Those are the very questions that science deals with ultimately.
Now, in terms of some areas of particle physics and the materials we're talking about, such as antimatter, for example, I mean, we've been talking about this now for over half a century. It's been around for a while. Dark energy and dark matter are relatively new.
Yes.
Can you explain what are they exactly? I mean, how do we describe them relative to other particles?
As I like to say, antimatter is not really strange. It's strange in the sense that Belgians are strange. Now, what do I mean by that? Go into a large room and ask how many people are from Belgium, and you won't get any hands put up. It doesn't mean that they're strange. You go to Belgium, everyone's fine. It's just you don't often see Belgians around. Same with antiparticles. They're identical to particles. If the universe was made of antimatter, it would be largely the same. You'd have anti-lovers sitting in anti-cars making anti-love under an anti-moon. And it's an amazing fact of physics that matter and antimatter are more or less identical. It turns out relativity in quantum mechanics implies for every particle that we know of, like protons and electrons, there must exist particles that have the opposite electric charge and the same mass. And we call them antiprotons, and the anti-electron we call a positron. It was an amazing discovery that came out of a theoretical prediction, actually. And the prediction was so strange that the person, Dirac, who proposed it, didn't even believe it. And it was only, again, the experimental discovery of antimatter and cosmic rays that convinced us it was there. But what's really strange is we appear to live in a universe that's essentially made of matter. There's not much more antimatter left. We can create it at accelerators. It's not just science fiction. We talk about it in Star Trek and other things, but we make antiparticles in particle accelerators and we smash them against particles. Because the interesting thing that happens when you have matter and antimatter and it comes together is they annihilate. And we use that to try and explore the fundamental properties of matter. And so it is a big mystery, by the way, and one of the things that particle physics is trying to deal with, to understand why we live in a universe of matter and not a universe of antimatter, or more simply, the kind of universe you would have created had you created a universe, or I would have, a nice, simple, uniform universe with equal amounts of matter and antimatter. That would be the most sensible universe. If that was the universe, however, we wouldn't be here, because all the matter and antimatter would have annihilated at the beginning of time, leaving nothing but pure radiation left. It would have been a beautiful universe, but a very boring one. And so, happily, that small asymmetry between matter and antimatter produced all of the history of the universe and all of the tragedy and glory that now makes human history possible. What is interesting is that we can take antiparticles, and could you make anti-atoms? Could you take an antiproton and have an anti-electron orbiting it to make an anti-hydrogen atom? We're just beginning to be able to do that. And then when we do that, we can explore and verify our predictions that these anti-atoms are exactly the same as regular atoms. If they're different at all, it'll tell us there's something fundamentally wrong with our particle physics theories.
And as we move into the new understanding with dark matter and dark energy, how do we distinguish those from these other particles?
Well, dark matter, people may say, look, it's like counting angels on the head of a pin. You invented all this stuff to explain the stuff you can't see. It's not real science. Well, that's not quite true. In fact, it's not true at all. In the first place, we've inferred its existence by weighing galaxies, so we know it's there. It's not just some invention of our minds. But more importantly, when we try and understand fundamental particle physics at the scale we're looking at the Large Hadron Collider, it turns out there are puzzles, and each of those puzzles to be resolved requires the existence of new particles, it turns out. So we're reasonably convinced there are new elementary particles in nature we haven't yet seen, and that's one of the things we're trying to explore at the Large Hadron Collider. It turns out almost every one of these theories which solves a problem in particle physics predicts the existence of particles which would be natural candidates for the dark matter in the universe. So it's a very interesting and exciting time because there are two different ways we might discover the identity of dark matter. One is by building experiments underground and waiting for this dark matter to come through the earth and bounce off detectors underground, and we're building them. In fact, one of the things I'm proud of is I proposed many of those experiments. But the other possibility is, instead of waiting to detect the particles that were created at the beginning of time, We might create them now in the Large Hadron Collider. So we might be able to create the very particles we're looking for to make up the dark matter. And so it's a race. Will we detect them first at the Large Hadron Collider or underground or neither? And we don't know the answer, and only time will tell. But we will ultimately, I think, in our lifetime, certainly know the identity of dark matter and know what is the dominant particle that makes up the universe. Dark energy is much more difficult. There's no experiments we can do on Earth to probe it. The only way we can probe it is by looking at the expansion of the universe itself. And that means that it's much more difficult to explain. And it means we're going to have a good idea rather than a good experiment. And good ideas are a lot harder to come by. A good idea may come in a decade. There may be a young Einstein listening to this podcast now who comes up with the idea a decade from now. It may be 100 years, maybe 1,000 years.
This is Up Close, coming to you from the University of Melbourne, Australia. I'm Shane Huntington. Our guest today is Professor Lawrence Krauss, and we're talking about the origins and future of the universe. So, Lawrence, I have to return to something that you mentioned before, and that is the concept of weighing a galaxy. How do you go about that? And when you do so, what do you find that's inconsistent?
Okay, well, it's very simple. You pick it up and you put it on a big scale. It's really very trivial. Actually, it's not so easy. But if you think about it, the way we weigh things is by using gravity. And we literally use gravity. In fact, the way we know the mass of the Earth and the Sun is by using gravity. Newton told us, for example, that objects orbit around the Earth, and the speed with which they orbit around the Earth depends upon the mass of the Earth. And in fact, by the way, that is exactly the way we know the mass of the Earth. We measure the velocity of satellites, including our moon, around the Earth as a function of their distance, and it tells us precisely the mass of the Earth. The same is true for the Sun. The way we weigh the Sun is by measuring the speed of the planets around the Sun. If the Sun were heavier, the planets would be moving faster. Using that technique, in principle, we could determine the mass of the Sun to 1 part in a billion. Turns out we can't with that accuracy because gravity is the weakest force in nature. Most people don't realize that. But gravity is so weak, it's very hard to know its strength exactly. We only know the strength of the gravitational force to 1 part in 100,000 or so. So that limits our accuracy of weighing the Sun. But physics is like Hollywood. If it works, copy it. And if it works for the Earth and works for the Sun, we use it to weigh the galaxy. So we weigh the galaxy by measuring the speed of objects like our own Sun around the center of the galaxy. Our Sun is at the edge of the galaxy. It's moving at 200 kilometers per second around the galaxy, orbiting it every 100 million years or so. And just from its distance and its speed, we can determine how much mass is pulling it in. And when we do that, we jump up and down because we discover by that technique that the mass of our galaxy is about 100 billion times the mass of our Sun. And when we determine the number of stars in our galaxy, it's about 100 billion stars. So everything hangs together, and you say, great. But to do a better job, you want to use many objects, not just one. And objects that are further and further out allow us to do a better measurement. And there are some objects further and further out. But the strange thing is, when we measure those objects, they're moving much faster than they would be if all the mass of our galaxy was contained in the visible region that we see. They're moving so fast that there must be more mass out there on scales larger than what we see. In fact, at least 10 times more stuff, and that's how we determine the existence of dark matter.
Lawrence, is it possible at this point that our overall model of the universe is just simply wrong and we are patching it up with these various ideas, or have we got enough evidence at the moment? We're on such a strong ride that it's unlikely we'll have to go back to the drawing board.
The fundamental picture of the Big Bang is really unassailable at this point. The evidence for not only the existence of the Big Bang, but the age of the universe comes from so many different sources, and it all agrees that it's really unassailable. But that does not mean we have a complete picture of the universe. Our picture of the universe is limited by what we can see. And first of all, limited by the fact that we only have one universe to test. There may be many universes, we can just see one. So there's no doubt when it comes to the very earliest moments of the Big Bang, times where we can't yet probe directly with experiment, almost anything goes. We don't understand t equals 0. We don't understand the very earliest instant of the Big Bang because we need a theory of quantum gravity to understand that very well. It's also true that on the largest scales, we are limited by the fact that we can only see as far as we can see since the Big Bang. So is our universe infinite, for example? A flat universe, mathematically, is an infinite universe. But we can't see infinitely far. So we don't know what happens on scales larger than what we can see. So our picture of the universe hangs together. We know we live in a universe that looks flat on the scales we can see. There was a Big Bang, and we can work backwards and test our picture back to maybe a millionth of a second after the Big Bang. But before those times and on scales larger than that, we really can't say for certain because we can't see, we can't measure.
When we think about the universe constantly expanding and changing, if we were to project forward, hundreds of millions of years and look out with the telescopes and so forth we have today, what would we be seeing?
Well, I've been thinking about that a lot, and it's amazing in a sense. It was kind of shocking and for some people depressing. What we'll see is nothing in a sense, because if the universe is accelerating, then all distant galaxies are moving away from us faster and faster. And eventually, believe it or not, they'll be moving away from us faster than the speed of light. Now, that sounds impossible because you learn in school that nothing can travel faster than the speed of light, but you got to be like a lawyer and parse that a little more carefully. Nothing can travel through space faster than light, but space can do whatever the heck it wants. And if it wants to carry objects away from us faster than light, like a surfer on a wave that's being carried out to sea, if the wave is going in the wrong direction, then that's fine. And so, in fact, what's happening is that objects indeed are moving faster and faster, and as they approach the speed of light, they'll disappear. And it'll take a long time, hundreds of billions of years. But eventually, all the galaxies outside of our local cluster of galaxies, which are bound to us right now, will disappear. And the universe will look in the far, far future much like the universe we thought we lived in at the turn of the last century. Because observers at that time, they'll discover quantum mechanics and electromagnetism and gravity and build telescopes. But when they do, they'll see an empty universe with one large galaxy in which they live, and the best picture of the universe will be a static universe with a single galaxy, which is the universe we thought we lived in 1900. And it's kind of poetic in that sense, but sad in a way that the evidence and knowledge of all of that we now see will disappear in a sense. But that should be sobering in a way. The good news, as I like to say, is that we live in a very special time. The only time in which we can observationally verify that we live in a very special time. But that's being facetious. What I really mean is that there may be things we could have seen 5 billion years ago, or things we'll be able to see in 100 billion years, which will change aspects of our picture, and that we have to have a certain humility. But it is indeed sobering to think that in the far future, the universe will have disappeared, essentially. And I use that, by the way, to try and argue in my own country with Congress to try and fund cosmology now while we still have a chance. But unfortunately, 2 trillion years is a little longer than the average lifetime of a congressperson, so that doesn't seem to have much impact.
Lawrence, you mentioned before this strong tie-in between cosmology and particle physics. Mm-hmm. If we come back down to Earth for a moment and just talk about the experiments going on in the Large Hadron Collider, as you know, there's been a lot of community concern with regards to these experiments. Given the lack of a complete picture of the universe, is there any issue with the sorts of experiments we're doing at the Large Hadron Collider at all?
No, essentially, because what people don't realize is there's a lot we don't know about the universe, but there's a lot we do know. That's what you have to remember. And, for example, while the Large Hadron Collider is the highest energy machine humans have ever produced, every second of every day, we're bombarded by cosmic rays from space that have much higher energies that are being produced in the Large Hadron Collider. They're so diffuse that we can't use them to test things. But the fact that, for example, if people are worried about creating black holes that swallow the Earth has been bombarded by high-energy cosmic rays for 4.5 billion years, and we're still here. The moon is still here. Look up tonight. You might see the moon. It's being bombarded. It's got no atmosphere to protect it. And so we often justify the Large Hadron Collider by saying we're recreating the Big Bang, but it's not a very big bang. What we're doing is producing energies over microscopically small regions to see what happens. But the actual amounts of energies involved are so microscopic that we're not creating a Big Bang. We're just creating an extremely small region which we can heat up to recreate the early conditions of the Big Bang. So there's lots of reasons independently to know that we're not going to destroy the universe with the Large Hadron Collider. So you can rest easy.
Lawrence, you mentioned before there are a variety of projects and areas where Congress and others in the US and I guess around the world have concerns about funding this type of work. What is the justification for funding this sort of work, especially the stuff that's down the very theoretical end?
As far as I know, people don't ask the question, what's the value of a Mozart symphony or a Picasso painting? Science is a cultural activity, and it's produced some of the most amazing ideas that humans have ever thought about. And The cultural value of science, of understanding where we are and where we come from, is the same as art, music, and literature. Great art, music, and literature forces us to reassess our place in the cosmos. That's what science does at its best. And if we are so impoverished that we have to stop asking questions about where we came from and where we're going, it's indeed a sad time. These are the most interesting questions that humans have ever asked. And by comparison to the money we spend on many other things that is, in my opinion, much more useless, the investment is very small. And so if we are at the point where we have to say, look, we can't stop asking these esoteric questions that change our picture of ourselves, then it's a sad time for humanity.
Can we also argue that, as is the case with many of the theoretical predictions made by Einstein over 100 years ago, we now have a variety of technologies that are in our homes? Is there hope that that's where this will head as well?
Well, you know, we can justify what we do by the technological spin-offs. And it's true. General relativity is esoteric, but you couldn't use your GPS machine without it. It turns out the effects of general relativity on the satellites have to be incorporated. If not, within a second, you'd lose all knowledge of where you were on Earth with the GPS satellite. So it's true that even the most esoteric ideas sometimes have technological spin-offs. But I think it is misplaced to argue for doing fundamental research just because of its technological spin-offs. The questions themselves have to be worth asking to be able to spend the money on. But having said that, it is absolutely true that our current standard of living vitally depends on the curiosity-driven research that was done a generation or two before. Things like the transistor. If you asked people to build better computers in the 1940s, they would have had wheels and cogs, and of course, the transistor changed everything. Discoveries come along that change everything when you didn't expect it, and they come along because you didn't know what you were looking for. And if we stop investing in fundamental research now, it is true that our standard of living, a generation from now, our children, the legacy we leave our children, will be much poorer. And in fact, it's one of the reasons why I argue that, to make an Australian example, since we happen to be having this conversation in Australia, it's important for Australia not just to live off selling its natural resources, but to think about the future, about doing fundamental research, because the countries that are going to be able to compete in the 21st century are those that invest in technology and ideas and research. So there is, of course, not just this altruistic, idealistic notion of understanding the universe. If we want to address the challenges of the 21st century, from energy to climate change, we need to invest in fundamental research now.
When we fall back to the issues around the universe and cosmology, where do you think we will be in, say, 50 years from now in terms of the big things that will come up?
I'm always worried about predictions about the future. And people always ask me, what's the next big thing? And I say, if I knew, I'd be doing it. But what I'm convinced of is that the most important things that we know 50 years from now will be things we had no idea about right now. Nature continues to surprise us in ways we could never have expected. Nature is much more imaginative than the human imagination is. And in order to make progress, we keep having to question nature, explore it, because it will yield those surprises that will change not just our picture of ourselves, but the way we carry out our lives.
Professor Lawrence Krauss from the Arizona State University, thank you for being our guest on Up Close today and giving us an understanding of how theoretical physicists measure and explain the universe.
It's been a pleasure. Thank you.
Relevant links, a full transcript and more info on this episode can be found at our website at upclose.unimelb.edu.au. Up Close is a production of the University of Melbourne, Australia. This episode was recorded on the 25th of August 2011. Our producers for this episode were Kelvin Parham and Eric Van Bemmel. Audio engineering by Gavin Neighbour. Background research by Deani Lewis. Up Close is created by Eric Van Bemmel and Kelvin Parham. I'm Shane Huntington. Until next time, goodbye.
You've been listening to Up Close. For more information, visit upclose.unimelb.edu.au. Copyright 2011, the University of Melbourne.